All right, so as Rick was saying, last November we had the opportunity to tell the world that we had made a big bet on RISC-V. I'm going to reiterate some of those messages for those of you who weren't there as well. What I'm hoping you get out of this is an understanding as to why we have become such strong proponents of RISC-V. Because if you really think about this, we are not a processor vendor, and we do not currently have any intent to be a processor vendor. So if you think about it, it's kind of interesting that for something that is all about compute and processors, that we made such a big commitment to RISC-V, even though we're not in the processor business. And so the reason for that is we think that there's too much focus that is put on the CPU, or the central processing unit, and we need the focus to be on the data. And that's kind of where we live in the ecosystem. And so for those of you who aren't aware of this, about half the world's data lives on Western digital devices. So we care a lot about the data. And so for us, processing, while very important, so I don't want to minimize the importance of processing, for us, processing is a means to an end, and the end is the customer's data. And so hopefully what you'll get out of this is understanding sort of how we think about data, and you'll start thinking about Western Digital as a data company even more so than as a storage company, and start to get some sense as to why we made such a big splash with RISC-V. So this is a legal requirement slide. I'll give you all the next half hour to read through this. I am determined one day to put a bug on this slide and give somebody a free SD stick for whoever finds it first. But this is the legal requirements that basically translates to, the very plain English version of this is, whatever I'm about to say, there is no legal commitment for me to do anything with it, okay? So that's what basically this says. But anyway, so as I said, we are all about the data. So let's put a little bit of context around the data and think about where does data come from. So if we go back many, many years, the primary role of data was a record, right? We basically kept our banking data, eventually supply chain data, inventory data, but it was data was primarily used as a record. And things got really interesting when networking came around and data started to be used as communications. We started using email, for those of you who remember the worlds of X.25 and X400 and those kinds of things. We really focused on data for communications. But more recently, data has been about efficiency. And you know, how many of you have sort of even bothered to use a paper map these days? And so don't raise your hand, you're not supposed to, okay? That was a test, no. But we all use our phones. It's all basically, it's all about efficiency, and the mobile world has really allowed us to use data to be more efficient as individual, to get from point A to point B and to accomplish our daily tasks much faster. But where data is going is data is the new currency. And oftentimes now you might hear the expression, data is the new oil. Data is how we make money, and the more we can monetize data, the more value it has to the business. And so now you should really start to get your hint of why does Western Digital care about this so much? Because remember what I said, half the world's data lives on our stuff. So the world has entrusted us with about half of their data, and we believe we sit in a great place to be able to help the world monetize that data. Because one of the other, I'll say, dirty little secrets about data is most of it is, the other term that's used is dark data. And dark data simply means I've accumulated a bunch of data, but I have no idea what it's for, what it's used, how to use it, or how to make anything from it. And so you can think about what we're trying to accomplish is, how do we turn dark data into money? And how do we do that? So one of the other really useful constructs around here is what we've termed big data and fast data. So let me put a few words around that, because most of you know I used to be at HP, and when I was at HP, I was living through the world of big data. And one of the constant battles that I fought at HP was the size of the data equals the value of the data. And this was a real trouble spot for me because it was all about the volume of data, the size of the data that you accumulate. And so I would come up with these funny little stories where I would tell people, okay, you just went to your neighbor's backyard barbecue and you took a video with your phone of their dog riding on a skateboard. It was like really cool stuff, you know, great video, you want to show all your friends. But over here you have your bank balance with the most recent transactions. So now I give you a choice because there's going to be a system crash. And you have to pick between the dog on the skateboard and your bank balance. Which are you going to pick? Okay, now you're supposed to know the answer, okay? Because I want my bank balance, which is about 100 bytes worth of information, even though that video is probably 5 gigabytes worth of data. And so the size of the data does not equal the value of the data. And so how do we extract and how do we discern those kinds of things? And so I had come up with these very fancy charts on the time, size, value of data. And because the other interesting attribute is while my dog on the skateboard might be interesting, its value decreases rapidly over time, right? My friends and stuff, they become less and less interested in my video of the dog on the skateboard the more days go by. And so my model of time, size, value of data was way too complicated. It was very uninteresting. It was weird charts. And so the team at Western Digital came up with this very simple construct. And yes, it's an oversimplification, but that's okay, of separating this notion of big data, where you focus on size of data, and you accumulate lots of data, and you use it for archiving, and there's a lot of applications, like you can see here around insight and prediction, but it's all about scale and size of data. But on the other side, and this is where the world is becoming increasingly more and more important, is on fast data. It's where you need the answer right now. It's not about the size of the data, it's about getting answers immediately. And obviously the easy example is if you have two autonomous vehicles driving down the road, you can't be in a position where both of them are going to wait until they send all of their telemetry information to a central cloud. They'll go do some computing for a while, then come back and give you the answer, because by the time they do, it's too late and those cars have crashed. So you need to be able to come up with answers very, very quickly. And so that is this concept of fast data. It's where mobility lives, where you need those real-time results, and more of this computing at the edge. So it's kind of funny because I lived through the decade of everything's going to the cloud. And now, you know, we kind of get everything into the cloud, and now it's all about how everything is moving to the edge. And that's why this notion of fast data is so important. So the thing is, in the process of doing this, what we noticed is that the world processing power was really focused on general purpose computing. And that was generally okay, because what was happening is, as we were taking advantage of Moore's law, we had enough compute power to use a general purpose computer to solve pretty much all problems. But what we've seen happening over the past couple of years is, with the Moore's law kind of tapering off and the companion Dennard scaling also limiting our ability to continue to scale, this notion of the lowest common denominator, that general purpose processor to solve all problems, was no longer going to work. And you're seeing this already, whether it's NVIDIA using GPGPUs in order to do machine learning when they started as graphics processors, whether it's Google doing the tensor processor work that they've done, or Microsoft with FPGAs. You're seeing more and more requirements to say, I need to accelerate my very specific workload. And so that's where we started to see where the energy was and where the world was going was, let's let the guys that do general purpose really well to keep doing that and keep doing that really well, and we'll kind of go out onto the edges where we live with big data and fast data and look at special purpose processing. And so this is the challenge you run into with general purpose processing, is that the general purpose processors, they're not evil people. They're not trying to make your life hard. They have a very difficult job, because when you're trying to develop the general purpose, you have to make all of these trade-offs that you think will solve the majority of cases. And so the general purpose processor vendors are basically making all of these trade-offs for you. They're telling you, here's the maximum amount of memory you can have, here's the kind of instructions you're going to have, here's the number of I/O lanes you can have on your processor, and so on and so forth. And they make all of those trade-offs for you, and they put also a lot of legacy overhead into the system. But their world is also very CPU-centric, not data-centric. And so this was basically the world that we saw needed to change going forward, was how do we break down the barriers of the general purpose to solve for the special purpose. All right, so for the first time, since we announced the fact that we're going to go all in with RISC-V last November, we're going to tell you about the cores that we have developed internally. So we didn't just stand on stage and say we love RISC-V and we think RISC-V is great. We actually put a team together and went and actually developed our own cores. We did that for a number of reasons, because we wanted to learn and understand exactly how RISC-V worked. As I said, we're not really in the processor business, so this is not something we're saying, hey, we're going to go commercialize and make available. You can never buy this, okay? But it was important for us to understand the details of how RISC-V worked inside. And so this is what we've built. So we've built a two-way superscaler. It's an in-order core, so that's kind of, we're at the low end of the spectrum, and 9-stage pipeline. And we made a lot of those choices and trade-offs based on our specific workload. Again, special purpose processing. We're building a controller for NAND or flash devices, and so we did a lot of analysis on what our workload did, but it gave us the opportunity to go do this. And the interesting thing, and part of the learning exercise, is we figured out that, well, doing the core was kind of fun. If I say it's easy, my engineers get mad at me. So they say it was fun, but the really hard part was all the uncore stuff. So it's all of the connections to the outside world that was actually the really, really hard part to do. And so right now what we're building is that we have 2 cores. We're building what I'll call a small and a medium, or a tiny and a small, depending on your perspective, for essentially consumer SSD applications. So think a client SSD that goes into your MacBook or your laptop, or USB sticks, that kind of stuff. And so you can see that we were able to use this core now to start connecting to the outside world, our ECC engine, and having direct access to the NAND channel path. So a lot of the benefits that we were looking at of RISC-V have really started to already materialize for us. So keep in mind here that we sort of went out on this publicly last November. We started not too long before that. And we're now already at a point where we are testing and validating these cores. I said at the summit last November that we expected to ship our first products with RISC-V in the early part of 2019, and so far we kind of appear to be on track for that. So this gave us a lot of freedom to go innovate both at the core level, but more importantly at the uncore level, and how these things connect together. So this is the punchline, and so this is, if you kind of do the, why is a non-processor vendor so interested in processors? And so this is the punchline. So if you go home with one thing, this is it. The reason we're doing this, and the thing we care the most about, and to all respect to the RISC-V, it's actually not the instruction set. It's about our need for open interfaces. It's about the industry's need for open interfaces. Because of this world of general purpose processors, as an industry, both in the embedded space and in the data center space, we're getting increasingly locked in to that general purpose model when we want to connect to the outside world. And so the idea of open interfaces at the embedded level, so we're not dependent or constrained on what somebody else thinks is the right interface to our NAND media, or on the open interfaces on the outside world in the data center where somebody dictates what kind of memory I can attach to my processor, what kind of I/O I can attach to my processor, and how can I attach processors together. By removing those restrictions, that's the real thing we're after. Because in the special purpose, we're not saying that they should stop what they're doing, we're just saying in this special purpose world, you cannot take general purpose constructs around the Uncore and the I/O architecture and bring that and be able to deliver the optimal special purpose case. You're always going to have those trade-offs, and where we're dealing with the incredible amounts of density of flash media and things like that, we can't deal with those constraints. So this really is the ultimate punchline for us, is it's about open interfaces and our freedom to innovate with those interfaces. Because as you saw, the general purpose world is about making a trade-off that says, if we use the real world analogy, everybody drives a four-door sedan. And we all know that the whole world does not live in four-door sedans. In fact, the whole world uses different types of vehicles to solve different kinds of problems. And so the same thing applies in our world, where we're trying to move from general purpose four-door sedans for everybody to saying, for this workload I need a jet, for this workload I need a big ship, and so on and so forth, because we can no longer tolerate this externally dictated of this amount of memory, this amount of I/O lanes, this type of connectivity, this performance, and so on and so forth. And so this is really where we got to the opportunity with RISC-V for us. And hopefully you'll get out of this a lot of why a non-processor vendors care so much about the processor ecosystem. It's because it's all about enabling us to create new opportunities around big data and fast data, but do it where the data lives. And so we care a lot about the edge and those kinds of applications. So I said, hey, we've spent the past 10 years really talking about big data, and those applications will continue. It's not like those applications are over, where we talked about this massive storage and the specialty processing around those big data applications. But a lot of the future applications and where the world is going is in what we've labeled as fast data and data at the edge. You know, your autonomous vehicle, aircraft engines, your mobile phone, and so on and so forth. That's where the processing of the future is happening, and where we need to really spend a lot of time, and that general purpose world just doesn't live up to the ability to do that. And so as we were looking at our options to do that, the openness of RISC-V was very attractive to us. You know, I like to say to people that I spent 31 years at HP. My last 5 at HP was doing a project called The Machine. It was all based on ARM. When I came to Western Digital, I had never heard of RISC-V. Okay, so RISC-V had been around for 6 or 7 years. I had never heard of it. So I did not come into Western Digital with an agenda to say, oh, I'm going to bring this RISC-V thing to Western Digital. In fact, it was the Western Digital team that educated me on RISC-V. And if I'm honest, my initial reaction was, yeah, whatever. Clearly other people have had that reaction too. So, but fortunately, we have some persistent folks who kept pushing this with me, and then I actually took the time to really understand what this was. And I had a pretty heavy background in open source. I had spent 5 years running HP's Linux and open source business. And so once I started to understand, I started to connect the dots between what had happened in Linux and the broader open source ecosystem and the opportunity that existed for an open processor environment. And that's essentially what got us really interested in the RISC-V world. And so we've all lived now for the past 10, 15 years. I mean, is there anything other than open source software these days? There are some, but I mean, the world right now is dominated by open source software. And there is an opportunity, if we do this right, to see the similar kinds of things happen. And these are just some examples of some of the various open source ecosystems that have popped up around there. And as I said, our increasingly data-centric applications are out on the edge, right? The world is really moving to, we need a lot of both processing and storage at the edge. So where all of our growth opportunities and where we're getting a lot of the demand from the customer base are things like surveillance applications and putting huge amounts of storage in a camera. But they don't want to just to have the ability to store the data at the camera. They want to be able to process the data at the camera. Right? So it's no longer this, I'm just going to take a camera feed, I'm going to stream all that, and I'm going to store that in some big data cloud, and then at some point, maybe in the future, I'll figure it out. It's the what's happening that's relevant now. And so those are the kinds of applications that we're seeing popping up everywhere that we're being called into. And so we're being pulled by our customers to say, hey, it's great that you have all this great flash media that you can store all of this data locally, but we need to do even more than that. And so that's what we're basically, the opportunity for us is to now bring increasing degrees of application capability right to the data. So think of now a storage device is now an intelligent media device that can do processing right at the device level. And so RISC-V really, when we sort of connected all the dots together, was the only thing that sort of opened up the opportunity for us where it solved the problem for big data, where we could do an increasing amount of compute right next to the data, and also went to the future and data at the edge and solving this problem of fast data and being able to go from very small processors to very large processors and open all of this up. But this is a journey, right? We are at the early stages. When I do the Linux analogy, all analogies are imperfect. You know, Linus started Linux in '92. IBM did a big announcement in '99 of spending $1 billion on Linux. We're kind of like about that sort of stage where RISC-V is growing up and ready for commercial, to be used for commercial viability, but we're still in those early stages, and we're not quite there yet. There's still a lot of work to do, and we're taking the risk to go do that. One quick thing also I wanted to kind of mention to folks is the notion of, we talk about open source and RISC-V, and this, you know, I could do an hour presentation on this alone, but open source software licenses and we often talk about open source, is not really in all cases applicable to hardware. And depending on how familiar you are with the details of open source is built on a foundation of copyrights. And all licensing is based on copyrights. And so when you get to hardware licenses, in some cases, copyrights aren't enough and you have to start looking at a patent portfolio. And for those who are staunch open source advocates, they abhor software patents, but very strong on copyrights. But on the hardware side, patents become increasingly important if we're going to protect an open ecosystem. And so this is to kind of show you a little bit of a chain of where the traditional open source software licenses can work, but there's some things to do. But some of the traditional open source software licenses are sort of orthogonal or don't quite apply to this world. And so this is another place that Western Digital is going to do some work, is try to make sure that we do the right thing to build some open source hardware licenses that really make sense for this world and build on that. One of the things that's often misunderstood in the open source world is this notion of permissive versus copyleft licensing. And I'm actually quite passionate about the fact that all open source licenses should be copyleft licenses. I think the only open source license that should exist is the GPL v2 and maybe AGPL to take care of some of the issues about web web hosting and those kinds of applications in the cloud. But the reason I believe that is because the thing that troubles me is people look at Linux and the Linux kernel quite specifically, and they say, we want to be just like the Linux kernel. Well, what made the Linux kernel work, and the reason why it got successful, was because of GPL v2. It's because it forced people to share and to come together as a community. And the troubling part about permissive licensing is that it lets everybody go off and do a whole bunch of proprietary things. They don't have to share, and it breaks a little bit of this sense of community. But right now we're kind of in a world where I have to be more practical about it, more pragmatic about it. And Apache has, it's one of the licenses I hate the most, but it's now become so pervasive that companies tend to gravitate towards Apache. And given the fact that for a period of time we're going to have to intermingle the open source RISC-V world with the proprietary intellectual property block world, and some of the software tool and tool chain, that we probably don't have a choice but to live on the left-hand side of this chart. But I'm hoping as time goes by, we can actually migrate some of our work towards the right-hand side. So again, I'll just skip through this. We kind of talked through this. So we really basically got to RISC-V can solve all of the various parts of the problem set we were trying to solve, from the fast data to the big data, predictive analytics to autonomous machines. Safety and security are increasingly becoming important. I don't know if they've come out. There's about 8 new flaws that have been detected since Spectre. I'm waiting to get the details. They were supposed to come out yesterday or today, and so I haven't gotten those details today. And so those kinds of things, Rob was saying, given enough eyeballs, all bugs are shallow. That's actually one of the things that I'm really looking forward to seeing, is those kinds of things not being an issue as we move forward into this ecosystem. And so that's why we put our weight behind RISC-V, and we told the world that we ship about 1 billion cores a year. Our plan is to transition those 1 billion cores to RISC-V. It's going to take a number of years, so this is not a tomorrow statement. It's going to take a lot of years for us to build out those products. You saw the first cores we're doing, first products in the first part of next year. And as the demand increases and as more people want to do compute close to data, we expect our need and demand for cores to double over that period of time. So these are the kinds of the things that we're doing to accelerate the RISC-V ecosystem. And so one of the special requests that I have from all of you is to also get very loud and very vocal about RISC-V. So I will continue to be a RISC-V cheerleader, but I'll tell you, one of my definitions of success is if I get drowned out by all the other companies talking about RISC-V and nobody has a clue who I am in the process, that would be a massive win. So if you're part of a company that's supporting RISC-V, even if you're in the early stages, even if you don't have definitive roadmap plans or you're committed to a particular product, please, please, please start talking about what you're doing, because the world needs to hear about it. The world needs to know that we're not the only ones that actually are implementing a real RISC-V core in a product that we will ship to customers. And so we really need your help in doing that so that everybody participates. It's great to see companies like NXP and others talking publicly about this stuff, and really helps everybody. So thank you very much for your time today. Hopefully you get a sense. Had a great time.
I think you may be getting at this, but do you envisage a future where people are really downloading programs close to or even into your hard drives and running on the data, very close to the data?
So yes, absolutely. That is ground zero. So we haven't figured out all of the details. So some of the things we've talked about just in a concept is what I like to call like an app store on the device, where we will have some sort of control engine to verify authenticity and the origination of data and all that kind of stuff. But being able to say, okay, I'm going to take let's say something silly. I want to do a face recognition thing on some surveillance data, but I want to do it at the device. So I'm going to take my algorithm for doing that, download it to what I've labeled the App Store, and let's just do it at the device. So yes, that's exactly what we want to do. I'm sorry, you had a question as well? Yeah. Sorry.
Thank you for the interesting talk. What role do you think will play the 128-bit architecture?
I'm sorry, I didn't understand.
What role do you think will play the 128-bit architecture?
Oh, what role is the 128-bit architecture? I don't necessarily have a great answer for that, but I will give you an answer. So when I was at HP, I was working on this project called The Machine. And my goal for the machine was to have a very large, unrestricted memory space. And the original machine architecture was delivering a main memory at 380 terabytes, okay? But my ultimate goal was for that to be infinite. In fact, one of the fun things I do at Western Digital is I tell them my goal is to eliminate storage. Very popular guy at Western Digital when you say trying to eliminate storage, because I believe everything should live in main memory. Everything should be a memory semantic. And so if that vision were to ever become reality, then I need to be at the exabyte plus range of main memory, which is where I would need 128-bit kind of evaluation. But I think we're a few years away, and I'll probably be dead, so when we get there, yes.
Are the cores that you described from Western Digital, are they your own design? I mean, your Western Digital's own design, and are you planning to open source those as well?
Great question. Thank you for that, because I forgot to mention that. So yes, they are Western Digital design cores, so we have a team that has designed those cores. As far as open sourcing, the team wanted me very careful, so I am making no commitments whatsoever as I do this. So we would like to open source the cores, and so the reason I'm not making that commitment as I stand here is because, as I said, a lot of the work we had to do was connecting to the uncore. And so in order for us to open source those cores so that they're useful to everybody to build on, we'd have to essentially, I'll say, sanitize or disconnect them from some of the proprietary uncore stuff that talks to NAND or our version of ECC and those kinds of things. And so we still have to decide, do we want to take the cores that we've designed so far and, I'll say, like I said, sanitize them to be able to be used as standalone, or do we want to essentially take a second generation of cores and design those from the ground up to be open source? But so the end goal is to absolutely provide not just cores, but other IP blocks as open source to the ecosystem. Yes. Any others? I'm hearing, oh yes, there we go.
Okay. To make a chip, you need to have EDA tools. There are three big vendors, Synopsys, Mentor, and Cadence.
Yeah.
Do you see a problem in that those tools are proprietary for implementing open source chips?
Short answer, no. It's kind of like, a proprietary Oracle database runs on Linux and everybody still uses it, right? So, or a lot of people still use it. And so using a proprietary tool chain to build open source things, I think is fine. I do think over time there'll be, I'm hoping largely in the university world, there will be an increased amount of incentive to maybe build an open source tool chain. But I'm not troubled by that, and in fact, I'd like to partner with them to support the RISC-V ecosystem. We've had some conversations. They obviously know what we're doing. We haven't been shy about that. So no, so I think they're great tools, and we should just use them. Yes?
Martin, thank you very much for your talk. I'm delighted to see you raising the issue of how you license open hardware. I wondered if you had any views, if you looked at some of the work on trying to craft open hardware licenses, like the CERN open hardware license, or particularly the solder pad license, which is relevant because it's what Pulp uses. I wonder what your view was on those licenses.
So the answer is yes. So we've spent some time, our legal team has spent quite a bit of time looking at that. And I believe CERN is planning a 2.0 version of the license to overcome some of the early issues. I'll confess that I'm drawing a little bit of a blank. There was an issue with CERN, the CERN 1.1 license in the open hardware world that kind of caused some issues. And like I said, I'm drawing a blank right now, so the specifics. But the CERN 2.0 open hardware license is actually something we're sort of actively looking at to go do that. And then you mentioned the other one. Again, I know we looked at it, but I don't recall the details behind it. But we do have a team that's looking at that.
Hi. I'm wondering, you have the implementation as pipeline. Do you have speculative branching as well in the implementation?
In this core?
Yes.
I'll give the short answer is no. So we do not have speculative execution. The reason why I say the short answer is we do some speculative work, but it would be a stretch to say we do full speculative execution on the core.
Mm-hmm. Would you might have similar problems in the future like Intel got and others?
It's an interesting question. We will, because we now have the knowledge of Spectre and Meltdown, we have the ability to ensure that whatever designs we come up with. But the challenge, of course, is that a lot of these things like speculative execution were designed to increase performance, but they're also the things that expose us. And so the question is, how easy is it to come up with an alternative design that overcomes the issues around speculative execution and out-of-order execution, and doesn't expose us to the issues of Spectre and Meltdown. So obviously we'd like to go do that, and the only advantage we have now is we don't have a legacy that Intel, ARM, AMD, they all have this legacy that they've built on this. We don't have that legacy, so we can build from fresh. And what I can't answer right now is we do not have a design today that gives us speculative, out of order, and solves Spectre Meltdown. So we do not have that yet. If we do, maybe we'll open source it. So. Any other questions?
A question about the here.
Oh, here, okay. Sorry.
A question about your SSD LAN controller chips. So there are two questions. First, you mentioned there are two types of CPU cores in the SoC chip, the main CPU and the data path CPU. So are these two CPU are the same or different? This is the first question. And the second is you mentioned that you made the instruction optimization for LAN, the media handling, right? So here the instruction optimization means you added customized instruction or optimize the existing instructions.
Oh, okay. So I get the two questions. So the reason we have so we've developed two cores so that we can use this kind of tiny and medium at different places, because we have, I only showed two up here. When we kind of look at all of our controller landscape, we have about 20 different cores that we use, and so we're trying to replace all of that with just one of the two. Okay, so those are two actual different cores. Now, as far as instructions optimizations for NAND media, the answer is both. So we're essentially running a profiling exercise to help us understand, first of all, can we optimize the microarchitecture and change the RTL to specific to the NAND media? Or do we need a separate instruction or two or three that is specific to our handling? And so the answer is both. In some cases, we're able to just optimize an instruction for our use case and the microarchitecture. In other cases, we add custom instructions. Okay? We're good? All right. Thank you, everybody.